Hello everyone, welcome back to a new session, Computer Science 2, MCS 2514. Today we are at week 2B. We're gonna go over chapter 9 and chapter 10, brief and quick. Then I'm gonna assign you homework 3 and project 2. Mind you, remember, homework 2 and project 1 are due Sunday 29th, midnight. So I have the book in front of me, and I'm on chapter 9, which is page 503. It starts by saying pointers, topic 9.1, getting the address of variable. So before we do that, let's define what a pointer is. A pointer is a variable that stores memory addresses. So you grab a memory address of other variables and you store it in a pointer variable. So the pointer variable points to the address of other variables. So how do I declare a variable and how do I store the address of other variables in it? The key operator is the ampersand operator. This ampersand operator you have seen before using references. So passing a variable by reference, you add the ampersand character. This way you're passing the reference of the variable. In other words, you're passing the memory address of that variable. How do I declare a pointer? You declare a pointer by specifying what data type you are planning to point at, for example, integer. Then you add the asterisk symbol. Then you specify the name. So for example, my PTR. Now this pointer is a variable that points to an integer data type. So it stores a memory address of an integer data type, and it can only store addresses for integer data types because that's what was specified when we declared this pointer. How do I store or initialize a value to this? It's a good habit to start by saying it's equal to null. This way, if I check against my variable and I check if it's null PTR, that means it's not pointing to anything, then I know that it has no value in it. Let's say I have my integer, and my integer is equal to 5. In order to store the address of this integer in my pointer, as I mentioned, I use the ampersand character. So ampersand my integer. This way, if my integer is at address, let's say 1000, then 1000 will be stored in my PTR. So if I display what my pointer holds at this point and the address of my integer, it's going to display the same value. If I run it, we're going to see that my integer is at address this, and the pointer is carrying this address. So this is what the pointer is carrying, and this is the reference of my integer. And notice they are the same. Now, what if I wanna, this is called referencing a variable. So I'm referencing a variable through my pointer. In order to access my integer through my pointer and get the value in it, which is 5, get it or set it. So I can access it to read it or access it to change it. I need to dereference my pointer, and I dereference my pointer using the asterisk symbol. So if I say display asterisk my pointer, this will display 5. See the 5? So do not confuse the declaration with dereferencing. If I'm declaring, I use the asterisk, my variable name, and then the value if I want to. If I'm dereferencing, I'm not declaring anything. I'm just dereferencing, basically putting that same symbol in the same fashion before the name, so I can do it like this as well. So it's this in the same fashion, same style, but instead of declaring, I'm just outing. So I'm using it alone with the symbol. This is called dereferencing. This will show me the value that the pointer is pointing to. The same way, dereferencing allows me to change the value in that memory address. So I'm changing the value that the pointer is pointing to from 5 to 10. So if I see out again, it will display 10 at this point. So 5, 10. I was able to access the memory address through the pointer, change its value. One time I accessed it and read the value, and another time I accessed it and changed the value. So the book starts by saying getting the address of a variable. The address operator, which is the ampersand, returns the memory address of a variable. So this fashion, this syntax right here returns the memory address of a variable. And then they draw a figure to show you how the memory address is continuous block of memories. You have a letter, 1 byte, then you have a number, short, and then you have amount, which is an integer. They show you how a letter consumes or allocates 1 byte or 1 slot, short 2 bytes or 2 slots, then amount 4 bytes or 4 slots. And notice the numbers of memory addresses. Letters start at 1200, then number is 1200-01, because a letter is only 1 character. Then the fact that number is short and 2 bytes, then the next address or the next available address is 1203. So 1201 and 1202 are allocated for the integer, for the data type short or the variable number. Then at 1203, we have the number amount or the integer amount, which consumes or allocates 4 slots, 4 bytes. So 1203, 1204, 1205, 1206 are allocated for the integer amount. Pointer variables. Topic 9.2. Pointer variables, which are often just called pointers, are designed to hold memory addresses with pointer variables. You can indirectly, like we did here, you can indirectly manipulate data stored in other variables. Now, the topic continues to show you how to create and use pointer variables. So this is how I created a pointer variable, and this is how I used it. I grabbed the address of another variable. It has to be of the same type. If I have a different data type, it's not going to allow me. For example, short, my short equals 10. If I say, hey, my pointer, I need you to store the address of my short, it's not going to allow me. It's going to say, hey, you cannot do that, illegal. This is different. I'm a pointer that points to an integer, but you're telling me to store a short. You cannot do that. So they have to have the same data type. And I'm going to explain in future why. We saw how we initialize using a null pointer. And if you need any more questions on how this is stored in memory, reach out or read figure 9-4. It shows you how pointer has its own let's call it it's a carrier. So it's a carrier, and you put an address in it. That address is for some variable in the memory that also has a value in it. So the figure shows 9-4. X is at address 0 times 7E00, and that X is carrying the value 25. So the value 25 is at memory 0x7E00. Then PTR, which is the pointer, is carrying that memory address, carrying 0x7E00. And then the example after that figure, which is program 9-3, is very similar to what we just did here. They are declaring a variable and giving it a value. Then they are declaring a pointer, giving it null pointer. Then they are grabbing the address of that variable and storing it in PTR. Then they are displaying stuff. At some point, at the last line, they change the value. They dereference the pointer, putting new value in it, and then counting again. Then they show you that you can do all sort of adding values, just like you did in normal variables. For example, I can do the combined assignment. So just like I do with variables, we can just do that. So this will add 10 to the existing value. This is equivalent to saying my pointer dereferenced equals my pointer dereferenced plus 10. So my pointer dereferenced is 5, just how we saw here. 5 plus 10 will be stored in dereferencing my pointer, meaning go to the memory address and put that value in there. Then they try to explain the relationship between arrays and pointers. There is one way you know how to display values with an array. And if you have an array and you need to access items and display values, you use the square bracket. Let me remove all these. Let's say you have short numbers equals 10, 20, 30, 40, and 50. In order to display items in my array, I use the subscript notation or the square bracket notation. So I do numbers at, for example, position 0 and L. If I want to display the second one, I can do at position 1. So this is the array notation or the square bracket notation. And remember from previous sessions, if I display only the name of the array, then it's gonna display the address of the first item, where the memory starts for the entire array. The memory starts at the first item. So this will display an address. So this can be stored in a pointer, but I'm not gonna go into it right now. Let me go just how the book does it. The book tries to tell you that the fact that number displays the first item, the numbers, since it's a memory address, plus 1 is different than saying 10 plus 1. 10 plus 1 is adding 1 to the value in that memory address. But memory address plus 1 means go to the next slot or go to the next item in the memory. So paint. The fact that this is short type, that means they each consume 2 slots. So I have here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, etc. Let's say this memory starts at 1000. So 1000 is right there. My array is 5 items. Each are 2 bytes because short data type. So 3, 4, 5. 1, 2, 3, 4, 5. So the first item is at address 1000. The second item is at address 12, which is here. The third is here. The fourth is here. And the last item is here. So 104, 106, and 108. So this whole slot or whole block has 2 slots, 2 bytes, has the value 10 in it, 10. Then this has 20, this has 30 as whole, 2 bytes for each. So 2 bytes, 40 consuming 2 bytes, 50 consuming 2 bytes. So if I'm dereferencing and adding 1, just like the previous example, I dereferenced my pointer and I added 10 to it. If I dereference this memory address and I add 1 to it, I would be adding 1 to the value 10. But without dereferencing, if I say 1000 as pointer or as array plus 1, that means go to the next item. This is why the compiler needs to know the data type with pointers. Remember, in computers, all memory addresses are of the same size, and that's why pointers are powerful, because you can point to any object or any data type with the same size of key, you can say. All memory addresses in the computer are of the same size. For example, 64 bytes. 64 bytes are from 0 to whatever, X. So whether you are storing a file, large file, small file, etc., you are grabbing a block of memory from 0 to X, which is the maximum for 64 bytes, as an example. You're grabbing a block of memory and putting the value of the beginning address in your pointer. So this is PTR. You're grabbing a value from 0 to X. This value 0 to X is always 64 bytes, whether it is actually 0 or the X. The size is 64, just like integers. Integers or unsigned integers, remember for our example, we gave it minus 1000 to plus 1000. If it's unsigned, that means it's from 0 to 2000. Memory addresses are unsigned. They start from memory address 0 to the maximum range. So whether the value in integer is actually 1 or 1999, 1 will consume 4 bytes and 199 will consume 4 bytes. So whether I'm at the beginning of the range or at the end of the range, I need the same size of bytes to store that value. Just like here, whether it's 10 or 50 or 1000 or 10,000 or 3 or 30,000, I always need 2 bytes. Similar case for memory addresses. In computers, whether you are at the beginning of the available memory or at the very end of the available memory, you will need 64 bytes to represent that memory address. So pointers will only consume 64 bytes to point to anything. Anything in the memory address can be pointed to using only 64 bytes. So back to my initial example, pointers are powerful because you can point to anything using only 64 bytes. Now, 64 bytes is also considered as an example because some systems pointers are 4 bytes. If older systems have shorter bus cables and memory addresses, so they didn't go all the way to 64. Let's say it's 4 bytes. Pointers consume only 4 bytes from 0 to some X. My memory addresses in my computer are 0 to whatever 4 bytes can hold as an unsigned. So if I need to pass a large variable between functions, instead of passing the entire object, copying it between files, let's say it's a 1 gigabyte file. Instead of passing 1 gigabyte file between my functions or my objects, I can pass only 4 bytes that point to that 1 gigabyte file. So making my program lighter in a way. So in here, when we do arithmetics with pointers or memory addresses, we are jumping to the next item. So notice this will display the address of the first item. This will display the address of the second item, not 10 plus 1. Same, this will display the first plus 2 items, so the third item. If I run, notice the addresses, they're gonna be 2 bytes different. This is 08, then you have 09 because each item consumes 2. So if I go here and I move this here, if 10 is at 08, that means it's consuming 08 and 09. In hexadecimal, after 9, we don't have 10. After 9, we have A. So then the second item, which is 0A, is consuming 0A, 0B. Then the third item is at C, D, and then E, F. Then we increment by 1 and we start over. So the fifth item is going to be at 1, 0. If I go back to my program and I stop this and I tell it continue to display them as series, now we can see it in a better fashion. So different addresses now because the compiler allocated different addresses. So 5.8, 5A, 5C, 5E now will increment and start over because the series has ended at F. This item 40 is at 5E and 5F, consuming 2 bytes. Then the second item is at 6061. So if I go back to my program, the address as is plus 1 means jumping over items. So if I do a relation between this notation and that notation, you're gonna see that arrays are pointers. Notice I can dereference, right? If I dereference this and then I surround or I wrap this address, right? It was displaying address. This was displaying an address, so I'm gonna wrap it with the parentheses. This alone was displaying an address, so I'm gonna surround it or wrap it with parentheses and dereference it. Remember dereference, what does? Dereferencing goes to that memory address and grabs or reads the value in that memory address. Again, if I surround and dereference, surround this address and dereference, surround this address and dereference, I will be displaying 10, 20, 30, 40, 50. This is an address and I'm dereferencing it. Then the address of the next item, dereferencing it. The address of the next item, dereferencing it, and so on and so forth. So it will display 10, 20, 30, 40, 50. The first 10, 20 are from this notation. So you have a square bracket notation and you have the pointer notation. This and this are equivalent. Then these two are equivalent. Then I can write down the equivalent for this and this and this. So 2, 3, 4. These are the sorry. These are the same. These are the same. These are the same. And these are the same. If I start over 10, 10, 20, 20, 30, 30, 40, 40, 50, 50. And this is the relationship between arrays and pointers. An array, it turns out at the end of the day, an array is a pointer. What else do you need to know? Yeah, that's what basically the book is saying. This notation is called pointer notation. This is the bracket notation. They do the same thing. The bracket under the hood is doing this. And in future, in this course, in future sessions, you're going to learn how to write your own method for the bracket. Meaning you can tell your variable or your object exactly what to do if some other function called the bracket. For example, imagine numbers is an object that has a size, a volume, height, width, name, color. Then you can write your own bracket for that object, and based on the number passed, for example, whether it's 0 or 1 or 2 or 3, you will display a specific member variable or attribute for that object. For example, if someone passes 0, I'm going to display the size. If someone passes 1, I'm going to display the width. If someone passes 3, I'm going to display my name. So something like that. You will define your own body or own functionality for this operator, and it's called operator overloading, and you're going to see it in classes. So the relationship between arrays and pointers concept: array names can be used as constant pointers, and pointers can be used as array names. You learn in chapter 7 that an array name without brackets and a subscript, which is this, actually represents the starting address of the array. This means that an array name is really a pointer. And then they draw some figures, how the memory address is in the memory. And then they show you in figure 9-6 how the pointer notation relates to the array notation. Then they go to topic 9.4, trying to tell you that you can do pointer arithmetics. With pointer variables, you can do arithmetics just like you do in with a normal variable. For example, say I have this array. I'm gonna keep it. It has these items. Then I have some pointer, short pointer LPTR. I'm gonna initialize it by saying it's null at this point. Then I'm gonna say, okay, my PTR is equal to numbers. Does that mean now LPTR is an array? No, it's not an array. It's still a pointer variable pointing to a short data type, but at this line, it will carry the address of the first item because the number name alone represents the address of the first item. So now if I see out PTR, we're gonna see the address. Then I'm gonna say, for example, int I equals 0, I less than 5 because I have 5, I plus plus. And on each iteration, I'm gonna dereference my pointer and display the value. Then I'm gonna say LPTR plus plus. Notice in my loop, I'm not manipulating PTR. It's only I from 0 to 5. So it's a loop that iterates 5 times. And I'm not checking against my pointer or numbers. It's just a loop that iterates 5 times. But the fact that I'm doing this will allow me to jump on the items. First time, it's going to display dereferencing the address of the first item. Then the fact that I incremented the address by 1, that means it's going to go to the next item, then the next item, and so on and so forth. So run. End line, yes. reference and then add. Yeah, so run. Why it didn't execute? Oh, I have shift by 1 to the left instead of less than. So 10, 20, 30, 40, 50, and this is the address of the first item. Now notice if I do how do we want to do it? For example, start by saying numbers plus 4 means the address of the last item, and then decrement. It's going to display it in an opposite order: 50, 40, 30, 20, 10. And I can do plus 5, jump 5 items. I can do plus 10, minus 10, minus 5. Yeah, so this is what basically is the book trying to say. You can do arithmetics. Then topic 9.5, initializing pointers. You can initialize pointer using null pointer like this, or initialize it with a memory address from an existing variable, or an array name. And they mentioned that they can't be different data type. Float my float cannot be pointed at with an integer pointer. The pointer has to be the same data type, because arithmetics need to know how many bytes it needs to jump or skip. If this is an integer and you add 1 to it, it needs to know that 1 is 4 bytes. Jumping 1 means jump 4 bytes in memory. If you have short numbers, short data type for an array numbers, and then you use an integer and it jump by 1, shorts are consuming 2 bytes, but jumping by 1 will skip 4 bytes. So it's going to be illogical. So that's why the compiler strict you to have it on the same data type. Then topic 9.6 asks you, tells you that pointers can be compared just by addresses. Of course, the address of the later is greater than the address of the earlier, and that's logical. If I can compare 2 pointers, but basically I would be comparing the memory address, not the values. If one address comes before another address in memory, the first address is considered less than the second. C++'s relational operators may be used to compare pointer values, and you can use all relational operators: less than or equal, equal, not equal, etc. Then they start by telling you that you can pass by pointers. So remember how passing by value work and passing by reference work. You can also pass by pointers, and it will behave the same exactly like passing by reference. Remember the difference between passing by reference and passing by value? Passing by value, the function can do anything with the parameter or the argument or the input, and it will not reflect in the caller function or the boss function because it was passed by copy. However, if you pass by reference, anything that happens to the value of that parameter or that input or that argument will be reflected in the boss function or the caller function. Similar to pass by reference, you can pass by pointer, and anything you do in that memory address will be reflected in the caller or boss function. How do I pass by function? It's simple. We create a function. For example, let's say this is my pointer, and then I grab this and I say display what? LPTR. So I have a function that doesn't return anything. It's called display, and it takes short pointer, right? Then I define it by saying, hey, you see the function declared above, it takes a input. it takes a short pointer called input, and it does this: a input plus plus. If I run, I'm gonna get the same behavior: 10, 20, 30, 40, 50. So I was able to access the memory using the pointer and then iterate. Notice now, I display, and after displaying, I'm gonna dereference a input and add 1 to it. See the difference between this and this? These are two different statements. They do different things. This will increment 1 to the address. This will increment 1 to the value that this address is pointing to. So this is an address. I dereference the address, means go to the value inside that address, wrap it, and add 1 to it. So add 1 to the value stored in this memory address. This is different. This is add 1 to this address, means now you're pointing at this slot, go point to the next, sorry, not slot. You're pointing at this item, go point to the next item, whether it's 1 byte or 4 bytes or 10 bytes or 15 bytes. What I want to show you is when we go back to this caller method and I display again, you're going to see that the value has changed. I'm not going to increment here. I just want to jump. So display will manipulate the data, and you're going to see that the caller function, main function, reflects that change because pointers are similar behavior to pass by reference. So go, it will display 10, 20, 30, 40, but on each iteration, it added 1 under the hood. Then in main, it reflected that change. Oh, the address at the first item now has the old value plus 1, the old value plus 1, the old value plus 1, because passing by pointer behaves the same as passing by reference. Then they go to the last, I think that's the last topic before dynamic memory allocation, which is in future, after test 1. We are not going to do dynamic memory allocation today. So this is the last topic. And they try to explain that there are 4 types of pointers. 4 types of pointers. You're going to have variable pointer to variable value, or variable pointer to const value, or const pointer to variable value, or const pointer to const value. So what are these 4 types? These 4 types are just how they sound. Variable pointer to variable value. Variable pointer to variable value means it's a pointer that you can reassign addresses to it as many as you want, and you can access or dereference it and change the value as many times as you want. Variable pointer to variable value. Then you have variable pointer to constant value. Means variable pointer means it means it's a variable that carries memory addresses, and you can give it a new memory addresses as many times as you want. However, you cannot dereference it and change the value because this pointer is pointing to constant values. Third type is constant pointer to variable values. Constant pointer to variable values means it's a pointer that carries one memory address only, and you cannot give it a new memory address. It points to one address and it will keep pointing to it. If you try to give it a new address, it's illegal and it's a syntax error and it won't compile. And it points to a variable value. So you cannot give it a new memory address, but you can dereference it and change the value as many times as you want. Then you have constant pointer to constant value. Means it's a pointer carrying one memory address only and you cannot change it. And you cannot dereference it and change the value. The memory address in that pointer is constant, and it's pointing to a constant data in memory. This number itself, numbers as a name, is constant pointer to variable value. Numbers as is, like this, see out, numbers, this as is constant pointer to variable value. Why constant pointer to variable value? Because I cannot give it a new address. It's illegal. It's gonna say expression must be modifiable L value. I cannot give it a new value. It's a constant pointer. However, I can dereference it and change its value. So it's a constant pointer pointing to a variable value. Whatever it's pointing to, which is the first item, whatever it's pointing to is variable value. You can access it, change it, do whatever you want, but you cannot change the address it's holding or it's carrying. So numbers or all arrays are constant pointer to variable values. So let's go over each type and show you the syntax. So variable pointer to variable is just anything like you have seen. So this is a variable value to, for example, I'm gonna give it the address of the third item. Boom. Right? This is a value at the third item using the square bracket notation, and I'm referencing it. I'm telling my compiler, give me the reference of the value stored in memory here. And it will grab the memory address and store it here. The same fashion I could have done by saying, hey, you see numbers? You see the address numbers? Jump 2 items and give me the reference of it. Or without the thing. So give me, so this and the previous are equivalent. This is right now, LPTR is a variable pointer to a variable value. I can go to LPTR again and give it a new address. It's not constant. I can say this time I want to carry this address. This time I want to carry this address. This time I want to carry this address. So it's a variable pointer. I can reassign memory addresses to it. I can give it one address, then I can give it a different address, etc. I can also dereference it and give it values. So it's variable pointer. I can give it a different memory addresses pointing to variable value. I can dereference it and give it different values. Variable pointer to variable value. Then we have variable pointer. So if you want to take a print screen or whatever, then we have a variable pointer copy to constant value. In order to specify that it's a constant value, C short, I'm specifying the data type. I specify it as const short. See how the errors popped up? The fact that it's a variable pointer pointing to a constant value, I cannot dereference it and change the value. It's created or declared as pointing to constant value, means nobody can dereference it and change that value that the pointer is pointing to. The error will say, hey, you're not allowed to do that. Expression must be modifiable L value. So this is the syntax for creating variable pointer to constant value. Instead of specifying short, you specify it as const short. If you want to take print screen, then we have constant pointer to variable value. Const pointer to variable value means this is variable value, right? Instead of short, now it's instead of const short, it's short. However, it's a const pointer. So the const now go between, oh, sorry, not here. After the asterisk. Oops. const. So it's a const pointer or to variable value. So the value is variable. The data type is not const. However, the pointer is const. It might be a little confusing, but you will get used to it. Now notice the errors. The errors popped up by saying you can, since it's variable, since it's pointing to a variable value, you can dereference and do whatever you want with the value. However, once you give the pointer one memory address, you cannot give it a different memory address. This pointer will carry one and only one memory address because it's defined to be constant pointer. Remember the example numbers? Numbers was created as an array. That means it's constant pointer to variable value. And the fact that I gave it a memory address, which is the address of 10, then doesn't allow me to give it any other memory address. For example, equals the address of numbers at 4. The fact that this is an array means that's a constant pointer to variable value. Means once I give it an address, I cannot give it a different address. Same fashion here. Once I gave it an address, I can no longer give it an address. But I can dereference it and change the values. If you want to take print screen, short, asterisk, const. Then we reach to constant pointer to constant value. And that is const short asterisk const. This is constant pointer to constant value. Means once you give it an address, you cannot change it and you cannot dereference and change the value. So this has to be modifiable and this has to be modifiable. Const to const. Why these are important? Because sometimes you work with code that you didn't write, or you collaborate with other teams, or you want to protect yourself from yourself. So even if you are writing the code for the entire program, you still need to protect your code from your own mistakes. For example, if I have a function that and remember in functions, every function, like I noticed in your assignments, that for example, you have a function that says pick a card or shuffle cards or whatever. You have a function that says pick a card. However, in that function, you are displaying. So that's not the right way to follow. It's not a good habit. Every function, the standard is every function should have only one job and one job only. And the name should reflect that job or that responsibility. So every worker function should have only one job and the name should reflect that job. For example, if you have a function that says pick a card, then that function should only pick a card, not display, not pick and display. So do not have a name different than the responsibility, even if you have only one responsibility. Also, do not have a function that have more than one responsibility. What I'm trying to say is, if you have a function called pick a card, don't let that function to pick a card and display and do something else. Only pick a card, pick a card, return the value. If you want to display, have another function that is called display. So the more you do, the more you follow this standard or this habit, the clearer your code is and the easier it is to debug. You know why? Because if you run your program, if you have a display function and a pick function and you are following the standard, and then you run your program and you see something wrong on the display, then you know exactly where to go. If something is wrong on the display, then it's the display function because that's its responsibility. If something is wrong in picking a card, then you go to the pick a card method because that's its responsibility. So this way you are pinpointing problems in your code instead of having everything in one function or more than one responsibility in one function. Makes it harder for you to debug because, oh, okay, something wrong, let me go to that function and then start from top to bottom figuring it out. So back to this. Why would I have different data types? Because sometimes I want to display. If I have a function that its responsibility is to only display, why would I give it variable pointer to variable value? That responsibility is only to display. It's not, it's the responsibility is not to change values. So I pass a constant pointer to constant value because the responsibility is to only display. Here is a pointer you're not allowed to change, and it's pointing to const. You cannot dereference and change. Sometimes you want to pass const to const. Sometimes you want to pass const to variable, means here is a pointer. Do not give it a new address. Don't let it point to something else, but you can do whatever you want in the data. So based on the business requirement or the logic of your application, you want to protect your code by choosing the right data type. And this is the end of chapter 9. We have 9.8, which is dynamic memory allocation, but we are not going to go over it today. We're going to go over it after test 1. Then we go to chapter 10. Okay, chapter 10 is more like knowledge than problem solving or figuring things out. In chapter 10, they just introduce you to what the language C++ provides you, utility methods to work with characters, C strings, and the string class. This is the string class, and it's different than C string. String is one thing, and C string is another thing. C string comes from the language C. String is the C++ string. So you have a C string for the C language, and then you have the string, which is C++ string. To use C string, you don't need to include any library. But to use the C++ string, you need to include the string class. Okay? What's the difference between this and this? C string is an array of characters terminated by a null. So char array has some characters k, k, h, a, l, I, l. This is a C string. Let me get rid of these. We're done. So this is a C string. C string is an array of characters terminated by a null. What's the size of this? The size is the number of characters plus the null character at the end. I can do this, or I can do, or let's see, C str, C str 2. And I can do it using literal, just by saying like this. The size of this is 7, and also the size of this is 7, because number of characters are 6 plus the null terminator. These are C strings. However, the C++ string is a class called string, L string, and I give it this. Now, this is not null terminated. It's a class. It has its own utility methods, its own behavior. I can add stuff. I can add two strings together. It's just different. They both represent maybe the same data type, which is bunch of characters. Whether it's one character or more than one character, they both represent stuff, but under the hood, they both behave different. So the book, or this chapter, chapter 10, tries to show you utility methods provided by the language to work with characters, C strings or the string class. Starting by character testing. The C++ library provides you several functions for testing characters. To use these functions, you must include the CC type header file. So if I include CC type, now this library will give me a bunch of functions that I can use to test characters. For example, if I move to the next page, table 10-1, it tells me you have a function called is alpha, function called is al_num, function called is digit, is lower, is print, is. Every method has its functionality. For example, is alpha is a method that returns Boolean whether the character passed is a non-zero number. So if the if it's an alphabet, then it will return non-zero number. يعني means true. If it returns 0, means the number is not an alphabet. If it returns anything other than 0, then the number is alphabet. Also, you have is lower, whether it's lowercase or not. So bunch of functions for you to work with characters. Hey computer, hey compiler, or hey program, I have this character. Is it lowercase or uppercase? Is it a space? Is it a function? Printable character is printable character is digit, whether it's a 0 to 9. If it's not 0 to 9, then it returns false. So this is a group. I can write them for you, but you can write them on yourself as well. It's not challenging. It's just, as I mentioned, info. Nothing to figure out. It's just a load of information that you need to know. 10.2 character case conversion also provides you with methods to convert characters. For example, from lower to uppercase, from uppercase to lowercase. And they show you, they demonstrate it. Then they go to topic 10.3, C string. Again, concept. In C++, a C string is a sequence of characters stored in consecutive memory location terminated by a null character. They show you a small graph how it's stored in memory. They show you a simple program how it's stored in memory. They explain that they are stored in an array, how it's stored in memory. You can see page 566, C++ at the beginning of the page, C++ space programming space is space create space, etc. You have null character at the end. Then they tell you that there are methods or functions provided by the language that allows you to work with array characters. C++ library has numerous functions for handling C strings. These functions perform various tests and manipulations and require the C string header file to be included. So if I go include C string header, now this gives me access to a bunch of utility functions to work specifically with C strings. Those functions are listed in the book: strcat, strcopy, strcmp, strcmp comp. And that's it. The list is on table 10-3, page 578. strcopy accepts two C strings or pointers to two C strings as argument, and the function copies the second C string to the first C string. The second C string is left unchanged. So if I have these two, let's say one is my first name and the second is my last name, and then I can do str copy. Here it is, str copy, and then I give it ctr, and then I give it cstr2. What this does is it's gonna copy from here to here without changing this. So if I run now and I stop here, buffer overrun, it's a small array. Oh, I can disable this warning, or I can just use the newer C++ way of doing things, _s for safe. Now if I run, buffer is too small. It's not too small. Maybe it's expecting a new input. So str copy, size, destination, size in bytes. What's the second one? Destination, source. Yes, that's what I need. Okay, let's give it, for example, maximum. So up to 20 bytes. So now C string has Khalaf in it. It had Khalil, now it has Khalaf. And the fact that I told it it's, well, the fact it's terminated by null, it knows where to terminate. So it terminated at here, KHALAF null. So this is str copy, and it's safe, the safe version of it because of the C++ 2020. Then you have strcat. It accepts 2 C strings and an integer. And the third argument, which is the integer, indicates the maximum number of characters to copy from the second to the first. So cat concatenate. It adds the second C string at the end of the first C string, and it accepts number of bytes for telling it how many to grab from the second one all the way to the last one. So str cat. Is there a safe method? No. Str cat 10. Oh, stop. Too many arguments? Okay, too many arguments, no problem. Are you gonna tell me that it's not safe? Okay. Function is S. Okay, fine, S. Here you go. Concatenate it for me. Abort. Okay, there is a different version then. Comma. So size in bytes, then source. Okay, if I tell it 10, you see I'm reading here. It gives me a hint. It's expecting destination, pointer to character, which is an array of character, size in bytes, how many bytes I want to concatenate, and then the source. So this is my source, concatenating to this only 10 bytes. Why? An invalid parameter was passed to a function that considers invalid parameters fatal. How? You just told me what to do. Buffer overrun while writing things. The variable size is 6 bytes, but 10 bytes might be overwritten. Okay, sorry, my bad. Maybe I need an update. Let's see how did the book write it down for concatenate. This is my string, this is string, size of this, my this. Concatenate. Oh, really? So the hint was wrong. Well. They are using concat. So let's disable the warning, just so I downgrade my version And it should be here somewhere. So I would go to project, properties, configure properties, C++, then preprocessor, then preprocessor definitions, edit, and I want to add whatever it told me to add. It was, what did it say? Cancel. This is not safe. You try to use, come here. Oh, CR. So output, use this to disable. So go here, copy, no, not here. Properties, here, and add this. Okay, apply, okay. Now go. So I disabled that error. Now, if I hover my mouse on this, I'm gonna see that it didn't do it. It did not do it. Oh, it did it on this. It concatenated this to this. Destination then source. Strange. So this is my destination, CSTR. This is my source. Anything else? Nothing else. Okay, let's give it 6. It's not gonna allow me. This is what the book is doing. Page 571, line 11. strn. Oh, strn. strn. Room. Really? Really? Okay, I'm gonna move on. I don't wanna stop on this. Maybe you can figure it out and let me know. This is different version than strcat, but I don't see why it's not working. I can't tell, maybe because of the version of my Visual Studio. Maybe it's too new for this, but I don't want to stop. Then but you have the list of functions that can work with C string. Then they go to topic 10.5, string and methods that allow you that the programming language provides you to work with the string class. The C++ library provides you functions for converting C strings and string object to numeric data types and vice versa. For example, if I have, I'm going to take this off and I'm going to take this off. Let's say I have the year, right? This year right here is bunch of characters 2022, bunch of literal characters. It doesn't mean 2022. There is no value as thousands. It's just group of characters. So these methods in table 10-4 are functions that provide you the definition or the functionality for converting a number C string to the value of it. So for example, L year equals ATOI, open, and then give it a const char string. I give it this. This method will convert this C string group of characters to the value of them and assigns it to the year. So now if I see out a year, it's gonna see out 2022, the value 2022 in thousands. Project, clean, start. Is it stuck from previous? Really? Disinfect, for sure. Strange. Very strange. No. The specific task could not be run. System. Maybe I did something to the permission of this program. Project. Rebuild. What happened to this program? Okay. I can't open the folder too. Okay, I'm gonna restart. Be right back. Okay, I'm back. I started. I know why it's asking me to run a scan. I've done this before, and this never happened. This will only disable the warning. So I don't think this is the cause of the problem. Something just got hang in the back. So back to this. So this function will take C string as a group of characters and convert it to the value of it. So if I run now, it displays the value 2022. As a matter of fact, this could be a nice problem solving for you. If you want to do a puzzle, something similar that you see in interview tests, they give you an array of characters and ask you to convert it to a number. So try that, and if you need help, reach out. Write a function that receives a C string and returns the integer value of that. And you should be able to figure it out. If you think about it, in your mind, you know that this is the least significant, this is the highest significance. So you can start from right to left by saying, okay, what is this character? Now this is 2. Then the following is 10, like the weight of it is tens, then hundreds, then thousands. So you are gonna convert this character to a number. Remember, C++ provides you methods to do that. We just went over them. Convert this character to a number and multiply it by the significance. At this point, the significance is 1. The next time or the next iteration, you are iterating from right to left. First iteration, you have a variable called significance, and it starts as 1. So convert this character to a number and multiply it by the significance, add it to some total value. Then on the next iteration, you multiply the significance by 10 and redo this process. What is this number 2? Multiply it by the significance. At this point, it's 10. Then it becomes 20 and add it to the total. So the total had 2. Now we have 20. So now the total is 22. Then jump. Now go to the next iteration. Multiply the significance by 10. So now the significance is hundreds. What is this? It's 0. 0 times significance is still 0. Add it to the total. So the total at this point is still 2020, 22. And then go to the next significance, multiply by 10. It was 100, now it's 1,000. Convert, so now 2 times 1,000 is 2,000. Add it to the 22 we have, so now we have 2,022. So if you want to exercise your mind, try to build that method. So back to the book. Topic 10.7, I believe. Yeah. What did we do here? We didn't. We're using C string. You know this already. We already used string, and it's telling you more about the string class, which is the C++ string way of doing or storing a group of characters instead of the C string. They give you a definition. The string class is an abstract data type. This means it's not built in or a primitive data type like int or char or characters. Instead, it's a programmer-defined data type that accompanies the C++ language. So someone built it and provides it to you with the language. They tell you how to read a line, how to compare string objects, and how to sort string objects. How to compare, you know that you can use relational operators with strings, and how to initialize. So we know how to initialize a string class. String l_my_str equals, for example, this. I initialized. I can initialize in a different way by saying l_my_str to constructor. And we're going to see this more. I can compare if l_my_str greater than l_my_str2. Do something. The way this comparison is going to work is not by length. It's going to go from left to right for each of the strings. From left to right, it's going to check the first character with the first character. Which character is greater than? If they are equal, that goes to the second character, third character. It happens that my name has the first 4 characters the same, so it will go to the 5th character. Is I greater than A? Yes, it is. I is greater than A. A starts, then B is greater than A, C is greater than A. The fact that I is greater than A makes my string greater than my string 2. So this will see out, yes, the condition is true. Yes, because I is greater than A. And then they show you they show you all the methods that you can do with the string, which is table 10-9. Look how many member functions you have provided for you. Append, assign, add, back, begin, C_s string. So for example, I can say I want a character array. So it's a C string, and this C string equals this string dot C string. So I'm converting. Let's see. Auto. Okay. So it had to be specific. It had to be const pointer, etc. So what this will do is this will convert string object to a C string array, add null to it, and assign it to my array. Then you have clear, compare, capacity, empty, end, find. You have a big amount of methods that are provided for you. So you don't have to reinvent the wheel. Anytime you're working with strings or C strings, you can just use what exists already. Then, oh, this is it for chapter 10. Okay, I'm gonna go ahead and post the homework, the project, and this session. Thank you, and let me know if you need